All right, 12:59. I can't wait anymore. Are you guys ready? So I don't have any syllabi or anything like that for you. I don't know that you necessarily need it. You are more than welcome to read it. The highlights of what is different between last semester and this semester. There are no essential outcomes differentiated from general outcomes. I would say that everything this semester is effectively a general outcome, and the same essential outcomes that you need to know how to do really well are the ones from last semester. So I don't think it's a surprise to say you still need to be able to draw Lewis dot structures and convert them to line angles and know what all of those things mean. You need to be able to do naming. You need to be able to spot a nucleophile and know what it means and what it does, draw arrows, resonance, stability of ions. So all those things that were the essential building blocks on which we built the course last semester, those are the same ones going into this semester. Hello, Timothy, how are you?
Hi.
Welcome, check, you are here. Thank you, thank you. So I hope that you guys will read through the syllabus, but if there's any questions, just let me know. You can email me or ask me before or after class, that's not a big deal. So the other thing is quizzes. I did change around a little bit the way, not the number of quizzes. You guys are still gonna have one regular quiz attempt on a Wednesday, followed by the possibility of 2 more retakes if you need them. So 3 opportunities at each quiz, just like last semester. What is a little bit different is that for a lot of reasons, primarily that I want to get feedback to you guys quicker than last semester, so that on Wednesdays or Thursdays during office hours, you'll have already gotten your quizzes back. You'll have already gotten the right answers. You already know what your score is, and you can come and ask me during those times. So the plan is that you guys, much like you have class on Fridays at 1, and those of you in Zoom, I guess most of you have class on Mondays at 1, and you know that we're kind of having class on both days, more or less. That your quiz will be Wednesday at 1, so from 1 to 1:30. Instead of just being an 8-hour block, you'll have a specific block. I know that Wednesdays don't have classes. I know that everybody knows that, and therefore you guys probably have a lot of other things going on Wednesdays as well. So if a Wednesday at 1 o'clock, you are not able to take a quiz and you know that in advance, let me know and we'll sort something out. You need to let me know in advance, because what we'll do is find a time earlier to do it. So either earlier in the day on Wednesday, or maybe like Tuesday evening or something like that. The reason to do them earlier instead of later is that I want to have answer keys posted, and I will grade them on Wednesday afternoons, and you guys will have all of your grades by the end of the day on Wednesday, so that you're ready to look them through and we can meet in office hours on Thursdays. So office hours will be the same times. Just go into Zoom, bring your quizzes, bring your questions, and we can go through them together. That is a really good way to fix any mistakes that you make and learn from them. Please bring me your questions. Please give me the opportunity to help you sort out things that you didn't get the first time. My office hours on Thursday are the same as the class periods. So 10:30 to 11:30, and then 1 to 2. Those are posted on Canvas. So it's the same Canvas link for Zoom. If you want to meet in a classroom and talk through things, we can try to figure that out. If you have class or something during my official office hours, let me know and we'll find a different time on Thursday to meet. I will make time and we will sort all of those things out. So does all that make sense? So that's our differences from last semester to this semester. It's mostly just the quizzes. For lab, we will start lab on Monday if you're in group A, Monday or Tuesday, or the following week if you're in group B. But a lot of the lab is going to be the same kind of way as last semester, which is that you'll be in lab half the time and there'll be some stuff to do outside of lab the other half of the time. There are going to be weeks when we all meet. We won't meet in the lab because there's not enough room for everybody. But the schedule for the labs for the whole year is already posted on Canvas. So feel free to go through and look at that whenever you want to, or just look 1 week at a time, whatever you choose to do. Any questions about any of that stuff? Okay. Hopefully, I usually find that the second semester of this class, while I don't want to say it's easy, is a little less daunting, because for one thing, I know that the way that this class is set up with quizzes and exams and things like that is different from most classes. And at this point, you've been through 1 semester of doing it that way already, and there's a certain level of comfort. Watching videos before class, I know you didn't have to do it. before today, but it's something you get in the rhythm of. And so I find that students are generally more in the rhythm of the second semester. And as I think that the learning curve in Organic 1 is pretty steep. And in the second semester, it is of course getting harder, but you're building on the same things. So hopefully there's more pattern recognition, and the amount of work you put in the first semester usually pays off in the second semester. We are taking this kind of 3-week aside to do spectroscopy, which is what we'll start on today. And spectroscopy is quite different from the stuff that we did in Organic 1. Spectroscopy is all about figuring out what an unknown compound might be based on basically graphs and light and the interaction of light with our samples. So it might seem a lot more like lab, which is fine. In class, we'll talk more about how to interpret these spectra and figure out what a molecule is, and we'll start on that today. But then about 3 weeks from now, we'll move back into naming and reactions and the kind of the similar stuff to what we did from last semester. It'll be new reactions, new functional groups, things like that. But it'll look a lot more like last semester, and hopefully the same kind of weekly pattern we'll get there. How you guys doing? Welcome back from break. I know that in general, there's this academic fatigue that sets in usually after spring break of a year of college. I suspect that probably your academic fatigue for the 2020-2021 academic year has already set in, and I'm sorry for that, but we're moving on anyway. I really want to be able to be here as much as I can for you guys, so please, if there's ever Thursdays where you need help, let me know. If there's ever just times in general that you need help, let me know. We can do this, you can do this. Today is gonna be a lot, I will warn you in advance. We're starting off strong, but you can do it. You can do organic too, all of you can. So that being said, welcome back. Let's do spectroscopy. We ready? Mallory, are you ready?
Yes, sir.
Mallory, you're going through the drawers of your roommate because you're not very nice to your roommate. And you find that bag of white powder. You want to know what it is. It's probably sugar, right? But what else could it be? Baking soda, exactly. So it's definitely one of those two things. And you don't know which one it is. So I asked you this kind of question last year in lab because there was one thing we did in lab last year to figure out what an unknown solid is. What was it? It was like week 2. There's a physical property, a little tiny instrument. You heated it up in a tube and melted it. Melting point, almost melting point. So melting point, we could get the melting point of an unknown sample and it would tell us one thing, which was melting point. Does that for sure tell you what the compound is if you had no idea? No, it just tells you the melting point. So it doesn't really tell you anything about the structure of the molecule unless you have every potential molecule in the little tiny jar to compare it to. So what spectroscopy is about is if we find or have an unknown sample and we want to figure out what it is, instead of just knowing one physical property, we would like to know more about the structure of the molecule. And using pieces of information about the structure of the molecule, we can figure out what a molecule is. And that's what we're going to spend the next 3 weeks doing. This is a whole lot like puzzles. And if you like puzzles, you'll probably enjoy this. I love puzzles. I love spectroscopy. If you don't like puzzles, sorry, we're doing it anyway, but 3 weeks from now, we'll move back to reactions and we'll get back into your comfort zone. Infrared spectroscopy is what we're going to do today. We're just going to talk about it today. You can practice it. You can review it. It's a lot of numbers and shapes to memorize, basically. But what it does is it tells you about the functional groups in your molecule. That's going to be our big picture of today. IR tells you about functional groups. Next Monday, we'll talk about mass spectrometry, and that's going to tell you a little bit about some members of your molecule. It tells you about halogens, and then kind of overall what's in there. And we'll just spend 1 day doing that. And then we'll spend the following 2 weeks, so the next 4 class periods, looking at NMR, which is nuclear magnetic resonance spectrometry. And that's going to tell us a lot about the carbon-hydrogen framework of a molecule. So none of those 3 things by themselves tells you everything about the molecule. But if you put together what functional groups are there and generally how big and how much stuff is in your molecule, and how are the carbons and the hydrogens put together. Using all three of those together, we can take an unknown sample, run these three experiments, look at the data, and it's a reasonably small molecule. We can figure out exactly what it is. And that's really powerful. And so that's what this is. It's like detective work. It's figuring out what a molecule is based on these physical properties and what we get when we put a sample into an instrument. What we're going to focus on today is really, this is a spectra that you'll get out of an infrared spectrometer if you put the sample in and basically hit go. We will in lab talk more about how this works. I will show you, we've got one, we will use it pretty regularly this semester. So we'll get more into the nuts and the bolts of how this works in lab. But for today, and for our kind of in-class lecture class, our goal is mainly to be able to interpret them. But really quick, infrared is one of the different types of light, right? Electromagnetic radiation. So there is UV, there's gamma, there's radio waves, there's X-rays, there's visible light, there's IR, all of these, it's a different spectrum. And you guys have all taken some physics at some point in your career. You've heard of these different things. Which ones come from the sun? One of them, you can see. What do we call it? Visible light? Yeah, that's what you guys are saying is visible light. So visible light is just one on this long spectrum of different radio waves and inversely different frequencies of electromagnetic radiation. Visible light is somewhere, let's just say in the middle. You can see visible light. You can't see electromagnetic radiation of higher frequencies or of lower frequencies. It's just this one little area. Would you drink after class, please? Yes, thank you. So it's with electromagnetic radiation, it's all about a specific frequency, and more or less is not going to do the same thing. So visible light, it's one small area and it causes one thing to happen. Interacts with molecules in your eyeballs, it causes a protein shift, which sends a signal to your brain and you say blue, right? Those are things that happen. UV radiation comes from the sun. What does that do? All right, I bet that somewhere along the line, you guys know what UV radiation does. Bad, we wear sunblock, we don't want cancer to our skin, all right, things like that. Briefly, what happens is that UV radiation will hit the molecules that have double bonds in your body, which the outside ones tend to be skin cells, and double bonds tend to be focused highly in your DNA. And therefore, it interacts with those double bonds and it shifts some things around, which causes chemicals to actually change. And if those chemicals are parts of your DNA, then you end up with problems which manifest or can manifest as cancer. So that's what we usually think about with UV radiation. Not more, not less, but that specific radiation causes that to happen. So those are two of the ones that come from the sun. Visible light, so we can see, UV radiation, so we can all die. And what else? What else does the sun do? I'll give you a hint, it's winter. It's not doing it well right now. Nobody knows what the sun does. It does, it heats you up, yes. And that's infrared radiation. So there's three main forms of radiation that come from the sun, pass through outer space, get to Earth. Visible, UV, infrared. They're all pretty close to each other. There's probably more, but it's not like we're getting a lot of radio signals from the sun or X-rays from the sun. Most of what we get is those three things. Excuse me. So what IR radiation from the sun does is very similar to what heat lamps do. It's above red. It's slightly lower energy than visible or UV. And what it does is when it hits bonds, it doesn't cause them to break, it causes them to vibrate. And that's it. And it turns out that the temperature any sample is corresponds to how much movement is going on in that sample. So we're going to do a quick experiment. You ready? Take your hand, put it on your desk. How does it feel? Is it the same temperature as your hand or does it feel colder? It probably feels colder, right? Because your hand is like 90 some degrees and the desk is probably like 60 or 70 degrees. Or if you're at home, I don't know what temperature your desk is, But if you leave your hand there, what's going to happen is your hand's going to warm up the desk, right? How does it do it? You're not melting the desk with your hand. It's not a phase change, but it's causing the molecules in the desk to start moving. And the same is true of UV radiation. It travels through space, through air, whatever. And when it strikes things, it causes the molecules to start moving. Right? But it's still, again, it's still a desk, it's still solid. So how can molecules move without being able to move around? In other words, how could you move without leaving your seat? Do it. By shaking your head no, that I'm not going to do it, you fell for my trap and you moved without moving out of your seat. Yeah, so there's all kinds of things and ways that molecules can move around without actually moving side to side. So we can have heat up solids or cool down solids, and that's what you did when you put your hand on your desk, right? If you move your hand somewhere else on your desk, you'll find that that spot is colder. You did it. You moved some molecules faster, right? So when it comes to molecules moving, there is side-to-side motion, and that's mostly what happens in gases and liquids. But with solids, what's happening more often is that they're just vibrating somehow. They're dancing without getting up. Right? So there are a lot of different ways that that can manifest. We have what's called scissoring, where a bond angle can vibrate. And we have stretches where individual bonds just vibrate, getting shorter and longer. We have some kind of motion like this. We have some simultaneous motion like this. And we've qualified all of those things. But in terms of what helps us with infrared spectrometry and figuring out what a molecule is, we're going to focus on this, a bond stretching. So if this is one atom and this is one atom, they just get a little shorter and longer, they just vibrate. So looking at this molecule right here, this is just something I've got left over from last year. We see bonds in here. We've got carbon-hydrogen bonds, we got carbon-carbon bonds, oxygen, so we got carbon-oxygen bonds. Each of those bonds is different and has a different bond length, which means that it will absorb energy, infrared energy, of a slightly different frequency in order to make it vibrate. So there is one particular frequency of light that will cause this bond to vibrate. More energy or less energy won't do it. In the same way that a specific frequency goes into your eyeballs and says green, more or less doesn't say green. So what we're going to do is we're going to go through and look at these different frequencies that cause different bonds to vibrate. And if that light is absorbed, it's telling us that that bond is present in our molecule. If the light is not absorbed, it tells us that that type of bond is not present in our molecule. And so what IR is really going to tell us directly is which bonds are present in our molecule. What we can do is take that information and figure out which functional groups are present in our molecule. So that's my really quick introduction to infrared. I will never quiz you on how an IR instrument works. Instead, what you need to be able to do is to look at a spectrum and tell me, what does this say about the nature and identity of the molecule? So what it will tell you is functional groups. That's what you'll be able to tease out of this. So that's what we're going to go through today, is a whole bunch of spectra. And we'll start with this one, but I'm going to write that down at the very top, which is that for IR tells you the presence or absence of bonds, which you can use to interpret the functional groups. And functional groups are hugely important. That's something that we learned about really, really early in being able to understand molecules, is what functional groups are present. And that's what IR is good for. It doesn't really tell you, it doesn't tell you how big a molecule is or what it looks like, what it's shaped like. It just tells you what functional groups are present or are not present. All right, so there's a lot of things labeled on this very first one. There's some rocks and scissors and stretches. But what we're going to do in this class is we're going to ignore rocks and scissors. We're going to ignore everything at 1500 or less. All of that stuff. We call that the fingerprint region. You can see it's written right down there, fingerprint region. Because a fingerprint by itself is actually not a good source of information. If someone steals your phone and then you find it later and there's a very big fingerprint on the screen, what can you do with it? You could take it to the cops and hope for the best, right? But it's a fingerprint. You can't look at a fingerprint and say, oh, there's arches right here. Chloe, stop stealing my phone. Instead, you would have to have a database to compare it to. Otherwise, you could use it to match to something you know, but it doesn't really give you clear information. So that fingerprint region is something that, much like a fingerprint, we're not going to learn how to interpret it. If, for example, you had a huge database, you could compare it to it, but we're basically going to just choose to ignore it. There's a lot of unclear things that show up there, and so we're going to let it go. Our clear or definitive stretches all appear to the left of 1500. So there's two things about this spectra, about IR, that are probably backwards from what we're used to. First off, we're really used to numbers starting at the left and going right. And these start at the right and go left. These are wave numbers. The unit on this is centimeters to the -1. Without getting way into electromagnetic radiation, you might remember that wavelength and frequency are inversely proportional. And so this is the inverse of wavelength. So this wave number directly corresponds to frequency. So these are higher frequency, these are lower frequency. And so that's basically what we are looking at. What we know about bonds and what this is going to end up with at the end of today, we'll revisit this again, but longer bonds tend to vibrate more slowly at a lower frequency. I'm sorry in Zoom, I know you're not going to be able to see this, but long bonds vibrate relatively slowly, but as you get shorter, they vibrate more quickly to a certain point where when it's really short, it has really high vibrations. And so way over here, way on the left, you have longer bonds that absorb light of slower frequency. And way over on the left, this is where we'll find our shorter bonds. They're the ones that vibrate with relatively high frequency. So all of this, what we're going to see today, you're going to memorize numbers and shapes, but really longer bonds are going to be over here and shorter bonds are going to be over there. All right. So when we look at this first sample, and all that this is, it's labeled here, this is octane. Octane, we start at 1500 and start looking to the left, you'll see that you have nothing for a while, nothing for a while, nothing for a while. And then you get to the second way that this is upside down, is that your peaks start at the top and go down. So your baseline is actually at the top. And that's because the other axis, which is transmittance here, transmittance means the light that is being passed through. And so our default is that the IR light is passing through or not being absorbed. And the default is that there's just nothing there. So there's nothing that absorbs light at 1600 or 1700 or 1800 or 1900 or 2000, et cetera, et cetera. So for this long area here, starting at 1500 and going up to about 2800, your baseline is at the top because all of the light is being 100% transmitted or passing through the sample. And then when we get to about 2800, there is something in your molecule that is absorbing the light. And so we see what looks like an upside down peak. And then it goes right back up again, and nothing is absorbed all the way to the 4000. So just kind of get used to thinking about these things as fully upside down, where nothing is at the top and peaks are dipped out. That's where light is being absorbed. So this right here is our very first example of there are bonds present in this molecule that are absorbing infrared radiation between 2800 and 3000 wave numbers, which are causing these specific types of bonds to vibrate. So it's heating up, specifically in this case, CH bonds. So what we can do is we can look at the spectra and say, there are peaks between 2800 and 3000, which tells us that light is being absorbed between 2800 and 3000. And I know, and you will soon know, that the types of bonds that absorb light between 2800 and 3000 are the CHs of alkanes. So sp3, which is carbons with 4 single bonds, sp3 CH bonds, vibrate quickly when infrared radiation of 2800 to 3000 is shown on them. Therefore, if you see peaks between 2800 and 3000, you know there are sp3 CHs, and so you can tell me that there are alkanes present in your molecule. That's what it is about IR. You see the peaks, they tell you that bonds are present, and you can take that information about bonds to make a statement about what functional groups are present. And that's how IR works. Does that make sense? So we're going to look at lots and lots of examples, but our very first one is that if you have peaks between 2800 and 3000, then you have carbon-hydrogen bonds that are associated with alkanes. So if you have peaks there, you have alkanes in your molecule. If you don't have peaks there, you don't have alkanes in your molecule. That's it. So thinking about what an alkane is, alkanes are really just long stretches of CHs and carbon-carbons. So I told you that IR tells you the presence or absence of bonds. So when you look at this little molecule, this is just propane, but what types of bonds are present in propane? There's 2. There's CH and what else? Yeah, carbon-carbon. So unfortunately, carbon-carbon single bonds, which would be the longest types of bonds that we see in organic chemistry, so they would appear farthest to the right. Carbon-hydrogen bonds are very unique, but carbon-carbon single bonds are about the same length as carbon-oxygen single bonds, which are about the same length as carbon-nitrogen single bonds. And so carbon-carbon single bonds usually show up around like 1100, and carbon-oxygen bonds usually show up around 1100, and carbon-nitrogen bonds usually show up somewhere around 1100. And so not only do they appear in the fingerprint region that has a bunch of other types of vibrations, but they all appear right about at the same region. So our goal of IR is to figure out what's present or absent. And since all of those things more or less show up right on top of each other, it's just inconclusive, and we don't worry about them because we can't use them for anything. So the only thing unique that does show up above the fingerprint region in an alkane is just these CH bonds right here. That's what we're looking at. So those CH bonds, this is for alkane CH. In other words, sp3 carbons attached to hydrogens. That bond right there vibrates somewhere between 2800 and 3000 inverse centimeters of absorbed infrared radiation.
So we're not naming the actual molecule itself. We're just trying to find the functional groups that are in the molecule.
Perfect. Exactly correct. So the one on the top of this first page is octane. You would have no way of knowing it's octane. The one at the bottom of this sheet is hexane. Notice that if you look at those things together, which is why I put them on the same page, the peaks are similar, but they're not exactly the same, because even in the fingerprint region, it actually looks pretty similar. But things are in different spaces because they are different molecules. But what you can say for sure is if you ignore everything to the right of 1500, all that you have is stuff between 2800 and 3000. So much like the top one, the bottom one has peaks between 2800 and 3000. And that's information you could use to tell me there's an alkane in this molecule. And that's it. This might seem silly, but furthermore, you could tell me there is not any other functional group present in the molecule because there are no other peaks that are absorbing IR radiation. So the presence of a functional group is really important information, but also the absence of a functional group is really important information. So this is an alkane, but Colette, it's just an alkane and that's all you know.
Gotcha. Thank you.
Thank you. All right, so that's a little space at the bottom of these. IR indicates the presence of alkanes with peaks where? (2800) to Owen, to what? 3000, exactly. And the unit on that is inverse centimeters or wavelengths. And those specifically are telling you about those CH bonds that are alkane CH, or more specifically, sp3 carbons attached to hydrogens. That's it. I know I keep saying that's it, and you might be getting excited because like that's what we're done for the day, but we're not. That's it for that page, and that's it for that functional group. All right, second page. Here we have alkenes. We're gonna do alkanes, alkenes, alkynes, and then we'll move on to some other functional groups. For alkenes, we have two bonds that are different from the ones we've seen already. So here's a generic alkene. It's got two different bonds that are new to us at this moment. One of them is it has a C double bond C. And a C double bond C should be shorter than a C single bond C. So a C double bond C will give you a vibration frequency or stretching frequency above the fingerprint region. And this one vibrates around energy corresponding to 1650 inverse centimeters. And I would say that these are all approximate. I would say that reasonably that's 1650 plus or minus like 15, 10, 15, something like that. But usually roughly around 1650. And that's where that bond would absorb light, to make that double bond vibrate. You also will usually have a CH coming off of that. You might remember from the fall, you might not. I'll remind you real quick. There is a difference between an sp3 hybrid orbital and an sp2 hybrid orbital and an sp hybrid orbital. sp3s were more p-like, so they were farther from the nucleus. sp2s are a little bit shorter, so they make shorter bonds. sp were more like an s, so they get even smaller. And then s is just the shortest, right? And then p was the longest. So this all corresponds, if you just want to memorize the numbers, you don't have to know that. But basically what's happening is that way over to the right, that like 1100, those were all sp3s. They make longer bonds because they were longer orbitals. Same thing was true of these bonds way over here to the left. What we'll find is that all the stuff that shows up here to the left of our spectra, these are all bonds to hydrogen because hydrogen is really small. So these are all bonds to hydrogen because hydrogen's the smallest, so it makes the shortest bonds. But the alkane is an sp3 carbon, a long carbon bond to hydrogen. sp2s are shorter, so the sp2s end up a little bit further to the left. So there's this magical number around 3000, where if it's less than 3000, 2800 to 3000, it's an sp3ch. But if you've got an sp2ch, which is the ch coming off of a double bond, it appears between 3000 and 3100. So an alkene tends to have both of those things. And so you will get peaks absorbing light at both of those frequencies when you have an alkene in your molecule. And that's what we see here. We have this peak right here, which is, in this case, it was 1642. It's pretty close to 1650. And that is the carbon-carbon double bond. As we move to the left, we see we have nothing for a while, nothing for a while, nothing for a while. And then we have stuff between 2800 and 3000. What is this, 2800 to 3000? What functional group? Alkane, right. So we do have alkane here. Technically, this is sp3 ch bonds. But then we also have this one peak right here that is around 3080. And this is our sp2 ch. Or if you want to think of it this way, it's an alkene CH bond. And so it's slightly different. Different is good. We really want to be able to determine what's in our molecule. So having information that corresponds to different functional group that we can see that is different is really helpful. If things all appeared on top of each other, we wouldn't know what's what, and then IR wouldn't be very useful to us. All right, the bottom one down here is a different alkene. So the one at the top is 1-hexene. It's 6 carbons long, the double bonds at the end. The second one is cis-2-octene, which are names you should recognize. It's 8 carbons long. The double bond is a little bit more in the middle of the molecule. So if you compare those two spectra, they look very different. But first off, we're going to start at 1500 and we're going to tune out all the stuff to the right of 1500. And then if we look at these two simultaneously, they start to look a little bit more similar. They both have a peak somewhere around 1650. It was 1642 in the top one. It's at 1660 in the bottom one. In the top one, it was pretty strong, strong meaning deep. In the bottom one, it was a little weaker and not as strong. But in both cases, you would definitely know that there are peaks there that are absorbing light. And in both of these cases, they're somewhere around 1650. And in both of these cases, that light is being absorbed because of the vibration of a carbon-carbon double bond. And in both of these, you don't have anything for a while. Sometimes you'll get these little blips in the baseline. I don't exactly know what that is. It's so short that we'll ignore it. But as you start at that point, you started at, I would always start at 1500. Ignore what's to the right of it, but start from that 1500 and start going left. Oh, we found a peak. It's at 1660. 1660 is around 1650, which corresponds to a C double bond C. Great, I've got an alkene in my molecule. And then I got nothing for a while, nothing for a while, nothing for a while, nothing for a while. And then I end up with a bunch of stuff between 2800 and 3000. 2800 to 3000 tells you the presence of what functional group? Okay, once again. Do you remember when we were first naming functional groups? And alkane was the very first one. And I cautioned you guys to not worry about labeling the alkanes in molecules, because pretty much all molecules in organic chemistry have alkane in it. And so when you guys were labeling functional groups, I always asked you to just ignore those. It's fine if you write them, but you can kind of ignore them because we know they're there because they're always there. The same thing is true of alkanes and IR. Get used to seeing 2800 to 3000 because it indicates alkanes, and we almost always have some alkanes. It's only really notable actually when that's not there. That's weird. But yes, there will be alkanes in most molecules. In addition to that, we saw that we have a double bond indicating an alkene. And as we go to the left, we had a peak around 3023. That's above where the alkane CHs would show up. And so you'd have to account for that. Well, that tells you that you have, this is your alkene CH. So this is the alkene CH. And this peak right here was the alkene C double bond C. Usually you'll see them both in the same spectra, because usually an alkene will have both things, the C double bond C bond and some CHs coming off. All right, so IR indicates the presence of alkenes with two things. Number one, you will have a peak around 1650 for the C double bond C. Number two, you will have a peak between 3000 and 3100 for your sp2ch, which means that you got that bond right there. So CH coming off of that. All right, that's two function groups. Only like 10 more to go. All right, next we see alkynes. Alkynes have, it's a kind of follow a similar trend. A double bond is shorter than a single bond. Triple bond is shorter than a double bond. So while single bonds appear usually over here around like 1000, the double bonds appeared at like 1650. The triple bond appears at usually around 2100 to 2200. So that C triple bond C bond is going to be between 2100 to 2200. And if there is an H coming off of your alkyne, because your alkyne is at the end of a chain, this bond right here would be shorter than the sp3 CHs. It's shorter than the sp2 CHs. It's an SPCH, so it's even shorter. It's even further to the left. These guys tend to show up around 3300. And so once again, alkynes can give you two different peaks. And here we have one of them. It shows up pretty clearly right around that. This one's 2119, but they appear somewhere between 2100 and 2200. And then you have this very clear peak around 3300. And those are the two peaks for an alkyne that's at the end of the chain, because it has two unique bonds. One is the C triple bond C, and one is the CH coming off of it. All right, Letitia, what's this stuff right here? Yeah, what are these peaks between 2800 and 3000? Okay, great. So we're all going to know for sure where alkane is. All right, I've got one more. Does that make sense for alkyne? It's just new numbers at new places. There is something I wanted you to be aware of for IR, which is that it has a problem for us, which is that if a bond is perfectly symmetrical, it doesn't appear in the IR. Thankfully, most bonds cannot be perfectly symmetrical. So any bond to hydrogen cannot be perfectly symmetrical because you got a hydrogen on one side and something else on the other side. A carbon-oxygen bond, a carbon-nitrogen bond, these things can never be perfectly symmetrical. The only time you can have a perfectly symmetrical bond is if the two members of the bonds are identical and everything attached to them is perfectly identical. And that's really rare. Even if it happened to a carbon-carbon single bond, we wouldn't know because the carbon-carbon single bonds show up in the fingerprint region and we ignore them anyway. So the only time this would matter is for a carbon-carbon double bond or a carbon-carbon triple bond. A carbon-carbon double bond, it's really rare because each of those carbons has two things attached and the chances of these two things and these two things being identical are pretty slim. But for a carbon-carbon triple bond, there's a pretty good chance that it can happen. All right, so for a carbon-carbon triple bond, they only have one thing on each side. And if those two things, the one on each side, are identical, then the triple bond won't even show up. And so this bottom one is just an example of how IR can fail you in this one specific circumstance. So don't go looking for this. But this is an alkyne that's perfectly symmetrical. So you've got a triple bond in the middle, and they each have a 3-carbon chain to the right and the left. So it turns out that it actually doesn't show up. And because there is no CH coming off of the triple bond, you also wouldn't have that 3300. Therefore, if you were to look at this spectra right here, what should you tell me you can say for sure? So ignore the triple bond. You would not have any way of knowing. Here's 1500. All that goes away. So Timothy, start at 1500. Tell me what peaks we see. Yeah. If you look at this, you should assume that it's just an alkane and nothing else. Don't go looking for problems. Go with the data that you're presented. And so that's all I would expect. I am never going to intentionally try to trick you. There is no way for you to not be tricked by this. Sound fair? The only way you could know is if you weren't just running IR. If you were also running mass spec and NMR. So it turns out that there's stuff that IR can't tell you, which is this. There's stuff that NMR can't tell you. There's stuff that mass spec can't tell you. They all have their issues. But when you do them together, you tend to figure out the pieces that were missing from one in the other ones. So this is a problem, but there's not much you can do about it. So it's not something to worry about too much. But IR indicates the presence of alkynes with, number one, you will tend to have a peak around 2100 to 2200 for your C triple bond C. And sometimes you will have a peak around 3300 for that SPCH. I say sometimes because if your triple bond is in the middle of a molecule, you won't have any H's coming off of your sp carbons. All right. How are we doing? Okay, it's just numbers. All right, quick pop quiz. Where did this CH show up? Right here, you just wrote it down. The CH of a triple bond shows up where? 3300, okay. Now we're getting to the fun molecules. This is what an alcohol looks like. An alcohol is OH. There are two new bonds for us that are showing up in an alcohol. One of them is carbon-oxygen single bond. But remember that carbon-oxygen single bond shows up in the fingerprint region, like all the CC, CO, CNs. So it doesn't help us. The only one that matters is we'll get this OH bond. And the OH bond shows up at 3300. Which might seem immediately like a problem. The CH of a triple bond shows up at 3300. OH shows up at 300 or 3300. Mallory, what's the difference? Look at this thing, 3300. Whoop. Look at this thing, 3300. Can you tell the difference? How so? Exactly. And OH is going to be across a wider span. It usually ends up looking like a strong, broad parabola. And that's extremely different from that CH peak, which was pretty short, shortish and sharpish. So a CH is always going to be sharp. Your OH is always going to be broad and smooth. So it's not just about the number where they show up, but sometimes it's also about their shape. So we're doing shapes and numbers today. So the OH shows up at 3,300, but it is a broad parabola. I will just draw right there. You can write out broad parabola. Broad. And that's it. So this is usually pretty easy to spot. It's far to the left. The OH of an alcohol is pretty unique. Even if you had a whole bunch of functional groups in your molecule, the OH, the alcohol peak pretty much stands alone, and it's pretty easy to determine. That's it. Just to make it even more complicated, this is an amine. An amine only has one unique peak, which is nitrogen-hydrogen bond. The NH of an amine shows up at 3,300 as well. But once again, its shape is very different. So the shape of an NH is that you can see it's wide and parabolic with kind of a spike coming out of it. This molecule right here, dipropylamine, is an N with only one H attached. If you have a molecule with an N and only one H, it ends up kind of being looking like that with like a spike sticking out. And if you have a nitrogen with two H's, it ends up looking like two spikes sticking out, kind of like camels. There's two humps and one hump versions of amines. And it just tells you how many hydrogens are there. But it's gonna be weak, meaning that it isn't a very deep peak. They end up being pretty short, upside down short. So they always stick down a little bit. But those little spikes tell you how many hydrogens are attached to your nitrogens, which is nice. And NH3 wouldn't show up because an NH3 is ammonia. It's never attached to anything else. So you wouldn't have to worry about those. These are our only options. So that's an amine. Questions on those? All right, moving on. The next couple pages of this are all about carbonyl containing molecules. So carbonyls are C double bond O's, and we have 5 different functional groups that contain C double bond O's. I know it's been a while since we did functional groups. Again, you'll have to refresh your memories on some of these. But the good news is that we can differentiate all of them. So even though they all have carbonyls, there are differences between ketones, aldehydes, carboxylic acids, esters, and amides. All of them have C double bond O's, but they all have other stuff that lets us know more than just there's a carbonyl. So the very first one is ketone. So this molecule, the top one on this page, is a ketone. Ketones have that C double bond O, but they have nothing else that is exciting or different. So a C double bond O actually shows up pretty close to where a C double bond C was. The double bonds are about the same length. C double bond C was 1650. C double bond O's show up around 1710. And they are strong. So a C double bond O is going to be 1710. I'm going to say approximately. Woo. It's approximately in that it's usually that plus or minus 10. And for a ketone, that's all you get. There is nothing else exciting about it. So if you were to look at this and start at 1500, we can ignore all of that. So ignore the fingerprint and start going from this point to the left. We've got our 1710, and that indicates a carbonyl. It's really strong because the C double bond O is really polar. It's really asymmetrical, so it absorbs light very strongly. It's the exact opposite of the peak disappearing because it's too symmetrical. All right, but then there's nothing else, nothing else, nothing else, nothing else, nothing else, nothing else, and then you see there's some alkane. And so that's what a ketone will have. It has a carbonyl and an alkane and nothing else exciting. With an aldehyde, you have that C double bond O, and you also have the CH coming off of it. So an aldehyde will also have your C double bond O, which will be strong and somewhere around 1710. So notice that in the one at the top of your page, the ketone, it was like 1718. This one's like 1720. But you will have the carbonyl in both cases because both of these functional groups contain a carbonyl. But the thing that this has that's unique is that CH. This CH is not exactly the same as an alkene CH. You've got a polar carbonyl that's pulling electrons away. There's a difference between those bonds. So when they vibrate, they'll vibrate at different frequencies. The CH of an aldehyde is going to give you two peaks. It absorbs light usually around 2725 and 2825. And they end up being kind of these two twin peaks that look something like that. So you'll have a strong 1710, which is what we see right here. And then you can probably make out these two peaks right here, a 2700 and a 2800. And that is the CH of an aldehyde. And an aldehyde will always have both, or all three if you want to, of those peaks. We do already have stuff that shows up at like 28, 25 normally, because that's where alkanes show up. But there's never another excuse of why you should see a peak at 2720 or 2725. I would encourage you guys, I've been doing it, but I'm going to just say it out loud, to start here at 1500 and work your way left. And you'll run into this first and you'll say, there's a carbonyl. And then at that point, knowing that there's a carbonyl and there might be other things, then keep going and look for the other things. For the one up here, we saw that there's a carbonyl. And there was no fancy stuff around 27 and 28. So that means that it's probably just the carbonyl of a ketone. But the one down below, we have a carbonyl. And as we go left, we see that there is stuff at 2700 and 2800. So that tells you that this is the carbonyl of an aldehyde because they go together. And then, of course, you also have alkane, but it doesn't matter. All right, our third carbonyl-containing functional group is a carboxylic acid. A carboxylic acid looks like this. C double bond O, and then an O, and then an H. So it actually has three bonds that might be unique. It's got a C double bond O, and we've seen C double bond O's already. Oh, sorry, it was responding to my hand touching it. Yeah. All right, so that C double bond O, where would you expect it to show up? Third time, same thing. 1710, yep. And then there is a C single bond O, but C single bond O show up in the fingerprint region, so that's not helpful to us. But then we do have the OH. All right, most of you at some point in the fall got a question wrong about an OH. An OH that's next to a carbonyl is not an alcohol. An OH that's next to a carbonyl is part of a carboxylic acid. And a carboxylic acid is very different from an alcohol. They're different in terms of reactivity, they're different in terms of acidity, and they're different in terms of where they show up in an IR. So the OH of an alcohol we saw already, I'm going to scroll back a minute. The OH of an alcohol was a lovely broad parabola centered around 3300. The OH of a carboxylic acid looks like this. Yeah, it is broad. It is usually kind of not very pretty and smooth, and it covers a huge amount of your actual spectrum. It usually goes from about 2500 to about 3500. So it's huge and it overlaps usually a bunch of other stuff, but it's very clear. And being very clear and obvious is really great for us to be able to tell these functional groups apart. So with the carboxylic acid, you'll have two things. You'll have the C double bond O of the carbonyl, which shows up at 1710-ish, and you will have your carboxylic acid OH, which is different from the alcohol OH. And that OH shows up between 2500 and 3,500 and tends to be broad and not very smooth. And those things go together. You need to have both. So what happens if you have a 1710 but you don't have this? Is it a carboxylic acid? No. So if you have a 1710 and you don't have any of those other things over here, it's just a ketone. You have the 1710 plus those twin peaks, it's an aldehyde. You have the 1710 plus this huge broad OH thing, it's a carboxylic acid. So that's how we can tell them. All right, we only have like 5 minutes, so I'm gonna go quickly through this. I didn't make a space here, but esters. Esters look like this, C double bond O, O, and then more carbons. Thankfully, these show up at a different spot. The carbonyl of an ester shows up usually around 1745. So it's higher than normal and you can tell it apart. Amides are C double bond O ends. Amides have consistently resonance structures. And so because of this resonance structures, which looks like this, that bond there, the C double bond O, is not really a double bond. It exists, like all resonance structures, as somewhere between a double bond and a single bond. And so the peak shows up somewhere between a double bond and a single bond. But the most stable of those two structures is the one on the left, where they're neutral. And so therefore, it's closer to a double bond than it is a single bond. And so a C double bond O shows up around 1710. A C single bond O shows up around 1100. A C double bond O with resonance shows up about 50 lower than normal. So the general rule of thumb is that resonance lowers IR peaks by about 50. So we would expect normally that a C double bond O is 1710. Well, in the case of an amide, it's usually around 1660 instead. So I would say 1650, 1660, something like that. Furthermore, amides have two things. They've got the C double bond O. They also have NHs. The NHs show up around 3,300. And we see them right here. So this is our fourth different time that we've had peaks show up around 3,300, but they're all going to be different. Remember that an NH for an amine was a shorty with little spikes coming out of it, and an OH was a lovely, broad, smooth parabola. For an amide, those NH peaks are kind of somewhere in between. They tend to be strong, but they tend to have spikes coming out. So they're kind of like an amalgam of the two. If it's an NH2, they tend to look kind of like this. And for an NH, they tend to look kind of like this. But they're strong, broad, and spiky. It ends up usually being pretty clear which one is which. Broad parabola around 3,300 is an OH. Kind of a strong, spiky thing around 3,300 is usually an indicator of an amide. But with an amide, it's nice that there's also going to be a 1650, 1660. So there's something else to look for. And then, of course, if they're just this little short thing with a spike coming out, that's an amide or an amine. So they're all different. All right, we're actually almost done, which is good because we're almost out of time. I did want to point out real quick, the amide carbonyl peak is 1650. 1650 was also where alkenes show up, but they're shaped really differently. The alkenes were just a tiny spike, and the carbonyls were always really strong peaks. So you should be able to determine the difference pretty well. All right, this is our last functional group. It's a nitrile. A nitrile is a C triple bond N. A C triple bond N is about the same length as a C triple bond C. Just for quick reference, a C triple bond C was 2100 to 2200. And a C triple bond N is somewhere between 2200 and 2300. And that's it. So those are all of your functional groups. That is IR. I don't have great tricks for how to learn these. Pretty much you need to memorize some numbers and some shapes. There are homework problems. I think there is no substitute for just, make some flashcards if you're into flashcards, but look at as many spectra as you can. So on that note, while our labs start next Monday and Tuesday, and technically if you're not in lab next Monday or Tuesday, you have an out of lab assignment, and vice versa. If you're in lab 2 weeks from now, then next week you have an out of lab assignment. The out of lab assignment that we're doing first is basically just more practice of IR and mass spec, which is what we're doing today and Monday. I would recommend that all of you work on that on Monday or Tuesday, whether or not you have lab, because it's questions that are really written about like how to interpret things and how to use it to figure out lab stuff. But that's what all of this is anyway. And if you're looking for more practice, which you should be looking for more practice for IR and mass spec, because really it's just all about practicing it, kind of memorizing these numbers. I would recommend you do that. You can use your notes. You're welcome to do it in a group if you want to. So please use it as extra study questions in addition to the one on campus. Does anybody have any questions? All right, real quick summary. IR tells you the presence of bonds, which tells you about functional groups, right? When we start at 1500, we ignore everything to the right of it. And then the stuff that shows up first, right in here, like 1600 to 1800, those are double bonds. C double bond C and C double bond O. And then we go to the left and we find in this region of like low 2000s, we find triple bonds. And then over here, all of these were peaks to H. So start here and work your way left. Every time you see a peak, think first we see double bonds, then we see triple bonds, and then we see bonds to H. So they're not just random numbers. They do go in an order for a reason. Thanks. Have a lovely weekend. Go Bears. You made it through one class. All right. Anybody have any questions? Any last minute after class questions? I'll close Zoom. Thank you all for coming today.